Hello everyone. Today's tutorial session is based on serial programming and I am Saurabh and I'm going to conduct this session for you. So now let's take a look at the contents that we'll learn today. The contents will deal with very simple topics like clearing the concepts of types of communication to some difficult topics like programming the UART module in the 8051 controller. The first type of digital data transmission is serial transmission, and what we can say is that embedded electronics is all about interlinking circuits, and in order for these circuits to exchange info they must share a communication protocol. So serial communication, if we go by the definition of that, it is a process of sending a stream of digital data one bit at a time over a single channel. Let's take an example of two digital systems wanting to transfer a data of 1011 in between them via a serial interface. So the green line indicates the wire, which is the channel. As the definition goes, one bit is transferred one by one and the rest of the bits follow the previous bit. So in this way, the digital system 2 received the data that was supposed to be transmitted. Now, let's consider a case of parallel communication between the same two systems. Parallel communication requires as many number of wires as there are number of bits. So this data 1011 has 4 bits, hence we require 4 wires. All the 4 bits are placed on each individual wire at the same time. Hence they travel at the same speed and reach the digital system 2 at the same instant. Now that we saw both types of communication, we can conclude that serial communication requires more time than parallel communication to transmit an entire block of data. But with regards to hardware complexity, serial communication outperforms parallel communication, and this is particularly beneficial where the number of pins available on the hardware to transmit and receive data are limited. Now let's take a look at the type of serial communication systems based on the mode of data transfer. Here we classify them as simplex, half duplex, and full duplex systems. In a simplex serial communication system, a single wire serves as the channel. It can be used only for one-way data transfer at any given instant of time. Then comes the half duplex serial communication system, which also requires a single wire and it allows data transmission and reception, but one at a given time. The single channel can be thought of as a multiplex channel for transmitting or receiving any data. The next one is the full duplex serial communication system, which uses two wires through which simultaneous transmission and reception of data is possible. We can assume a full duplex communication system to be a two-wire simplex communication system. The next part is going to be about synchronization. When two or more than two entities synchronize, they occur simultaneously after fixed time instance. In synchronous serial communication, a clock signal synchronizes with the data which is to be sent or received. So a single clock can be synchronized with multiple data streams, and hence at least two wires are required to communicate, of which one is a clock and the other will send or receive data. While in asynchronous method, no clock is used. Instead, the data frame is modified by concatenation of some extra bits. This frame can be transmitted over a single wire, hence a single wire suffices the need. Now that we have understood the different system of communication and the different ways to serially communicate, we will now learn something about the speed of communication. A common problem is that many a times we confuse bit rate with baud rate. Bit rate is the number of bits that are transferred per second, whereas baud rate is the number of symbol changes per second. I'll clear this out with an example. If we consider an NRZ digital TTL signal, that is a not returning to zero digital TTL signal, we will have three voltage levels: plus 5 volts, 0 volts, and minus 5 volts. So these levels will define three symbolic constants, whereas a bit in this case would mean a transition from plus 5 to minus 5 volt. So we conclude that the baud rate will be twice the bit rate. Conversely, if the signal was just between plus 5 and 0 volts, the bit rate would definitely be equal to the baud rate. So this was a very simple difference between the bit rate and baud rate, which is very commonly confused. We have now prepped ourselves with the very basics. So let's plunge into the most versatile IC, that is the 8051 microcontroller. The 8051 microcontroller is an 8-bit controller working as a CISC, that is complex instruction set computer, with 111 instructions. It has an Harvard architecture, which means that there are different memories for storing code and data. Our main focus, which is going to be on the UART module along with two timers. The UART module supports four modes of communication with support for multiprocessor communication. Timer 1 is usually engaged to generate the required baud. The transmit and receive interrupts acknowledge the completion of data transfer. So this is the block diagram of the 8051 UART module. RX and TX control block form the heart of the UART module, and the timer 1 clock is divided by 2, or it is left alone by the SMOD bit present in the PCON register. We'll come across the registers that we need to study in at a later stage. So as you can see, the timer 1 overflow rate is divided by either 2 or is left as it is, and it is given to the divide by 16 block of both the TX and RS control block. At this point, we'll just ignore the T clock and R clock and assume them to be at the value 0. So, considering the transmission control block first, the divide by 16 counter divides the input frequency by 16 and gives to the TX control block. The data which is to be transmitted is given to the SBUF register by the C51 internal bus. Depending upon which mode is used, this TB8 bit is enabled and it can be put in this D latch and can be used further. Modes 2 and 3 employ the use of this TB8 bit, whereas in mode 0 and 1 this TB8 bit is not used. So when the user asserts this write to SBUF signal, assuming that this TB8 bit is used, this tri-state buffer will pass this TB8 bit value to this D flip-flop. The D flip-flop is connected to the 8th bit of this 0 detector, and the D input of this flip-flop is grounded. When the shift signal toggles, the data in the SBUF is shifted by 1 bit towards the right. At that point, the T flip-flop also shifts the data, that is the TB8 bit, into the 8th bit of the 0 detector. Now this bit later on is taken into the SBUF, and consecutively all the bits are shifted to the right one by one. Consider the first bit, which is shifted to the right on the first toggling of shift signal. When the first bit is available at one of the input of this AND gate, only when the data bit is 1, the bit under consideration at this AND gate is transferred to this OR gate. Now the significance of the send by signal is such that when this signal is 1, the TX line is pulled up to logic high level, and when it is negated, whatever the data is to be transmitted is given to the TX line. Every time that a bit is shifted towards right, it is going to be a 0, since the D flip-flop is having a 0 volt in. Thus, on every right shift, a 0 gets filled in the SBUF register, and the 0 detector block gives the signal to the transmission control block only when all the bits in the SBUF register are 0. When this signal is received, the TX control block sets the TI interrupt, and we get an acknowledgement that the data which was to be transmitted has been successfully transmitted. Now let's see what happens inside this circuit when there is reception of data. Firstly, to receive data, we need to detect the start bit. So the RxD pin is connected to the 1 to 0 transition detector, which will detect the start bit. Once the start bit is detected, the further bits are put in this bit detector, which is controlled by this Rx control block. The Rx control block is also clocked by this divide by 16 counter, which is run by the timer 1 overflow. The RX control block initializes the input shift register with a value of 1FFH. This is a 9-bit data wherein the use of the ninth bit can be avoided. So as and when the consecutive bits are received, they are put in this input shift register, and also a signal is given to the RX control block about the number of shifts. Once the number of shifts are over, that is a total of 9 bits are shifted, then the RX control block won't give a shift signal to the shift input shift register, and the data which has been captured is written to this SBUF, which can be only read and written to the C51 internal bus. So okay, I hope you guys are okay with this functioning of the logic. Now we move forward to understand some of the very important registers in the functioning of the UART module. The first one is the SCON or the serial control register. Starting from the LSB, the RI and TI bits are the receive and transmit interrupts, which are set by the transmit and receive control block. The RB8 bit is the ninth bit which is received during reception of data. The TB8 is the ninth bit which is transmitted during transmission of data. The RN or receive enable bit is supposed to be asserted so that we can successfully receive data. The last three bits, which are SM0, SM1 and SM2, decide in which mode the UART block operates. The SM2 bit, if set, makes the controller operate in multiprocessor communication mode, whereas SM0 and SM1, by their combination, we can know in which mode do we want to make the controller function. The next register is the TMOD register. In this register, the bits which are important to us at this stage are TR1 and TF1. More information on this TMOD register can be found in the previous tutorials. The TR1 bit, when set, enables the timer 1 to run, and the TF1 bit is the timer 1 overflow bit. The TH1 and TL1 are just 8-bit registers which are written with the 8-bit value for the timer to run and generate the baud. The PCON register contains the SMOD bit, which is of utmost importance to us. The SMOD bit enables the doubling of baud rate in mode 2 as well as in mode 1 and 3. The next part is to know about the baud rate and the formulae. In mode 0, we get a fixed baud rate which is of FOSC by 12. In mode 1, the baud rate is variable, which is determined by the formula 2 raised to S mod into FOSC divided by 32 into 12 into 256 minus TH1. Mode 2, in that the baud rate can be fixed to any of the two values. In mode 3, the baud rate determination is exactly similar to that of mode 1. The only difference is that mode 3 uses multiprocessor communication. Here you can see a general frame while serially communicating with any device. A mark indicates that the TX line or the RX line was initially held high, the start bit. Then comes the data, 8-bit data, and again is a stop bit. Now let's learn something about the modes and their operation. So the first mode, that is mode 0. Mode 0 is a simple 8-bit shift register mode. The clock is given through the TXD line and the data transfer takes place through RXD. It has a fixed baud rate as previously said, and there is no need to configure any timer. Mode 1 is a completely functionable full duplex UART mode. Baud rate is variable and is set by timer 1, and it is a 10-bit data frame which consists of start, data and stop. Mode 2 is an 11-bit communication mode. The frame is constructed as the start bit, the data, the TB8 bit and the stop bit. The TB8 bit, which is present in SCON, is user programmable and sometimes is used to denote the parity of the frame. In mode 2, there are just two baud rate values which can be changed by setting or clearing the S mod bit. The last mode is mode 3, which is a multiprocessor mode. For this, it is necessary to set the SM2 bit, and it is also an 11-bit mode of communication. with the frame being start, 8-bit data, TB8 and stop. Now I think we have gained enough knowledge to try out a program on serial communication. In this program what we do is we take user input from the PC, and for every input that is given we control a LED on the 8051 pin.